Okay, students, today's topic is simulation of radioactive decay process. Okay, here in case of radioactive decay process, N is actually here N is actually the number of nuclei, radioactive nuclei, which is present at any time t, and these radioactive nuclei can decay randomly and spontaneously. Okay, so according to the radioactive law, dn over dt is proportional to minus n. That means that the number of radioactive nuclei decaying per unit time is proportional to the number of radioactive nuclei which are present in time t. Okay, so dn over dt is proportional to minus n. Okay, so here the proportionality sign can be, you can say, finished by involving the equality sign here. In that case, dn over dt becomes to be equal to dn over dt is equal to minus lambda n. Okay, here dn over dt is the rate of decay, right? Rate of decay, that means number of radioactive nuclei decaying per unit time means how many nuclei decay. Let's say in unit amount of time. The unit amount of time might be second, might be millisecond, might be microsecond, and so on. The number of years and so on. And here, when n is equal to n naught, right, at the start, n is equal to n naught at the start. So, and at any other time other than t is equal to 0 at the start, or other than t is equal to 0, and might be other than n naught, right? So here lambda is the proportionality constant, which is specially named as decay constant, because this gives us information about the decay of the number of nuclei per unit time, per unit, you can say, available number of nuclei for decay. Okay, so here lambda is the number of nuclei, decaying per unit time out of the available number of undecayed number of nuclei. Okay. In this case, for the radioactive decay law, that is the iterative equation becomes Ni plus 1 is equal to Ni minus lambda Nit. And by using this iterative equation, a graph of this kind can be obtained in this in which it is seen that number of nuclei, let's say, decrease with the passage of time. Okay, the same aspect can be well understood by using the simulation of this process. Okay, let's go to the simulation. Here in this case, you can put here any number of nuclei at the start. Okay, so here, let's say at the start there are 1,000 number of nuclei, and you must know that these number of nuclei can decay totally, you can say, randomly and spontaneously. Okay? So if we press this button for initialization, and number of nuclei will be initialized at the start, and then those radioactive nuclei will start decaying. Okay, we can look at. So that here the red circles are actually representing, you can say, the number of undecayed radioactive nuclei, and with the passage of time and the decay, the white circles are actually representing those number of nuclei which have decayed with the passage of time. So in this case, so you can see here the graph of a number of, you can say, remaining, you can say, nuclei which have to decay with the passage of time versus time here. So here it is graph, the number of remaining nuclei and the time t. Okay, so here the important point is that the number of nuclei which are present at any time t, they decay totally randomly, and you can say spontaneously. Spontaneously means no external agent, no external factor can affect the decay. So and random means any you could say nucleus can decay at any time. We cannot predict that which one nucleus will decay at what time. Okay, so from here you can see this spontaneous and you can say random nature of radioactive decay process. Okay, thank you.